Okay, next let's consider a different knowledge transfer task, which will be multitask transfer. That is, we train on many tasks that we cannot control, right? Not like domain adaptation. We train on many different tasks, and then we would like to transfer the knowledge that we obtain over many tasks to a new task. And for that, we're going to examine model-based approaches. We're going to try train a general model that might be valuable for the different tasks. We'll see model distillation. We can distill knowledge from various tasks. And lastly, how we can build modular policy networks that then we can mix and match for different tasks. So far we saw that more diversity in either the policy that we train for the source task or the domain than in the source domain. This results in better transfer, but we need to somehow design this diversity. For instance, by in simulation to real-world transfer by randomizing the simulation, right, as I just discussed. What happens if our task is to transfer from multiple different tasks? So in a sense, again, this is what we're going to discuss now. In a sense, this is closer to what people do, right? We build, when we come to solve a new task, we build on a lifetime of experience. However, such transfer is usually harder. Past tasks don't directly tell us how to solve the tasks in the target domain. They might be vastly irrelevant, specifically over a lifetime of experience. So first we're going to explore model-based reinforcement learning. If the past tests are all different, and we cannot control them, right? So we just are trying to build on our lifetime of experience. What still do they have in common? What does our past experience have in common with the new task? So in many cases, the laws of physics are the same, right? In a specific, in a very general high-level domain, right? Same robot doing different chores, have mostly similar physics in the world around it and also in its operation. Same goes to a car driving to different destinations. And in general, video games with similar controllers maybe, though that might have less in common. But still it has some physics in common. So a simple solution here would be to train a model on past tasks and then use it to solve new tasks, right, as we've seen before. A more complex version would be to adapt or fine-tune the model to the new task. So this would be easier than fine-tuning the policy. In cases where the tasks are very different, if the tasks are very different, then the policy has a very hard time adapting. But for a model that would be easier, specifically if the physics are mostly the same. So again, this points in a case where the model of the environment is mostly the same, however the task is completely different. Then trying to transfer a policy might be very difficult, but that's not the case if we just try to transfer the model. And this is the idea behind the paper One-Shot Learning of manipulating skills with online dynamics, adaptation, and neural network priors. Another approach would be to solve multiple tasks with the same policy. Okay, so to train a very robust policy initially in our target tasks, we'll try to train a very robust policy. So sometimes learning a model is very hard, so some models can be very complex in very complex environment. So in some cases we're targeting to learn a multitask policy that can simultaneously perform many tasks. So we're trying to train a policy that captures many sub-policies, right? So it's not a high entropy policy. It's not a high entropy objective on a specific task, but it's a very diverse policy. It's a single policy, but that can solve many tasks. Okay, so it's an expert policy, but very with diverse expertise. It's something conceptually different than a high entropy policy for a single task. So one idea, an intuitive idea and something that can help you understand the difference between a high entropy policy. If we're trying to train such an expert policy, a policy that is expert on a variety of domains, one solution to that is to train it on a unique MDP. And the MDP that we're defining is an MDP that is defined via all of the source tasks, all of the past tasks that we've seen previously, right? Or in a video game, it's all of the Atari video games. So we train it on all of the source tasks that might be relevant. But in order to define this very, very robust policy, we say that we have an initial state in our MDP, S0, where we don't have any action to choose, or we only have one action and do nothing, I don't know. And then there is a transition probability that is distributed over all of the possible tasks, right? So we have, each task is a different MDP, and our initial state simply is makes the choice, or randomly picks one of the MDPs, and then we solve it. And now we have one high-level MDP that encompasses all of our tasks. If we optimize a policy on this generalized MDP, then the policy is hopefully an expert to some extent on all of these tasks, right? But I'll show you later, this solution is actually doesn't perform very well for deep neural networks, for training them, due to the high correlation. Once you pick an MDP, then you have a very highly correlated samples, and it can pull your policy into one direction that is most relevant to the MDP that was less trained on. A different approach to solve this issue would be to train on each one of the MDPs separately, and then somehow, we'll see how, to combine the different policies into a single policy, to a single expert. So the way to do it was presented in this paper, distilling the knowledge in a neural network. The idea here is to train an ensemble of models. Training a single model, as I said before, are often not robust. Instead we train on many models and average their predictions. This is the main idea behind ensemble training. This is currently how most machine learning the strongest machine learning model in competitions win, by just training an ensemble of those and then averaging their predictions. However, this is very expensive in test time, because you now have to query many models. And that in many cases might not be applicable in reinforcement learning, specifically if we would like to work in the real world, if we would like it to actually perform in the real world. So we would like to train a single model that is as good as the ensemble. Ensemble, the set of neural networks, we would like to train a single neural network that is similar in performance. So the way to do this is through distillation. We train on the ensemble's prediction. That is, we take all of the output of all of the networks. So for instance, if we train several policies, we just take the distribution of the outputs of these different policies, and we'll train the target of our distilled network. The target of that network would be the ensemble's predictions, but as a soft target. Okay, not just the majority, but we will try to capture the distribution of the outputs from all of the ensemble. The intuition here is that more knowledge in soft targets, there's more knowledge in soft targets, right? There's the full distribution, than in hard labels, and that might be beneficial specifically in RL, right? When we actually would like to have these high entropy predictions. It can be very helpful for us. So indeed, this is the idea behind the paper Actor Mimic, Deep Multitask and Transfer Reinforcement Learning. where they try to train a general policy to play all of the Atari games, or a variety of Atari games. So they write that given a state from a source task, SI for instance, as a specific domain, we define the policy objective over the multitask network as the cross entropy between the expert network's policy and the current multitask policy. This is how they define the actor mimic network policy, right? And this is the loss function for that actor mimic generalized policy. In contrast to the Q-learning objective, which recursively relies on itself as a target value, we now have a stable supervised training signal, the expert network output, to guide the multitask network. So again, they use the distillation approach to train a single generalized policy to play all of the games. So indeed, here you can see some results comparing the actor mimic approach against DQN agents. And you can see how the performance here compares to a DQN agent, to a simple DQN agent, but also to the best DQN agent out of the ensemble. That would be the yellow line, and the purple line would be the mean of the DQN agent. And you can see that the actor mimic approach might not perform best, obviously, in all cases, compared to the best DQN agent, but it performs pretty consistently across the different games. And again, this is the same, a single policy that is trained to play all of the games. So these are pretty impressive results, where you can train a single expert to play the different games, right? And usually with DQN, you have to train, obviously, as we've seen before, and as you saw in your home assignment, you have to train it specifically for each domain. And here they can show very impressive results where they can train a general expert.